Hello, this is Peter Foy, Senior Technical Marketing Manager with GigaDevice, and welcome to my series on embedded MCU design. Hello, I'm Peter Foy, and welcome to my second video on Embedded Builder. Today we're going to concentrate on the graphic configuration tool that's built into Embedded Builder. Again, Embedded Builder is our free IDE to develop with our GD32 MCUs. So there are a plethora of tools, development tools for GD32 development. Today we're going to concentrate on the Embedded Builder tool. It's our free IDE, and it supports all of our ARM-based devices as well as our RISC-V-based device families. So today we're going to concentrate on going through the graphic configuration tool. But again, Embedded Builder is based on Eclipse. That allows you to do your code editing, compiling, debugging, and programming of your device. But today we're going to concentrate on the graphic configuration tool. So this graphic configuration tool allows you to assign your pins, configure your clock tree, whether you're using external oscillators or using the internal oscillators. And then you can basically configure your dividers and multipliers based on the peripheral needs. So again, there is a third tab. So there's three tabs within the tool. The last tab is your peripheral configuration tool. Allows you to adjust your vector interrupt controller, DMA, GPIO, analog if you have it, etc. within the device. After you configure the device graphically, you'll go in and you'll generate the code. So the code generator will create HAL firmware libraries for you, and the HAL firmware libraries will be based on, again, your pin, clock, and peripheral configurations. So to date, the graphic configuration tool is supported in the E230 family of devices as well as the F3X0 series of devices. But we're working diligently to include all of our device families within the graphic configuration tool. So this is what the screen looks like in the Embedded Builder tool when you bring up the graphic configuration tool. Again, you can assign pins in here. You can configure your modules in the pinout tab as well. Then there's a clock configuration tab and then a configuration tab for the peripherals. So let's go ahead and take a look at the device that we're going to be using today. So on the evaluation kit I'm using today, it's going to have the F310 device on it. It has a Cortex M4 core on it. It also has a floating point unit. This entire family has a floating point unit in it, as well a memory up to 128K of flash, 16K SRAM. It's got connectivity, a nice set of connectivity in this device family as well. The 350 has some enhanced connectivity in it, a TSI, touch sensing interface, HDMI port, and also a DAC and a couple of comparators. This family supports or comes in 6 different package offerings. So let's go ahead and take a look at where this sits in the F3X0 series. So the F310 is what we're going to be using today. It has a 72 megahertz clock. There's an F330 that runs at a higher clock rate and includes an enhanced timer. And then the F350 runs at an even higher clock rate and includes all these other peripherals as well. So we're going to be using the F310 C8T6, comes in a 7x7 LQFP48 package and has 64K of flash and 8K of SRAM. So this is a screenshot of the evaluation kit. It includes through a USB port a USART. We're going to be using these 4 LEDs today. It also includes a double EEPROM that's hooked up to I2C port. There is an infrared LED for a receiver and an LED for transmit. There's 3 keys or buttons on the board. There's a rheostat that's connected to the ADC for evaluation there as well. I2S ports connected to a headphone jack. And then there is a SPI quad flash or a NOR flash on the board as well that's connected to the SPI port. And then also there's a TFT LCD display on the board, and we will not be using that today. So the demo that we're going to be putting together today is going to use the 4 LEDs, and we're going to configure those GPIO for those LEDs, and then we're going to generate a simple LED chase demo in the software. So again, the GD Link debugger is built into the board, so you don't have to buy that separately. So all our eval kits and starter kits have that GD Link debugger built in. And so let's go ahead and get started. All right, let's go ahead and launch the Embedded Builder tool. Select the workspace we want to work in. So this is what the IDE looks out like when you open it. There's a splash screen that shows up here. It goes through basically what you can do with the tool here. On the left-hand side, you can see where you can create a project. You can import projects. There's the programmer under GD Tools. And then also the Embedded Builder user manual is at your fingertips right here in the tool as well. You have access to all the data sheets in the tool. User manuals are also included in the tool. Demo suites for each one of our device families you can download, as well as the firmware libraries. So today we're just going to go ahead and create a project. So let's give it a name. And then select next. So the only MCU families that are going to show up here from Create GD project are the families that are available for the graphical configuration tool. So we can select the 310 here. We're using the C8T6 device. So I'll select Finish here. So immediately after we select that device, the first screen that pops up is the graphical configuration tool. So there are 3 tabs in the graphic configuration tool. There's a pinout tool that includes all the modules. You can create pinouts here, manually select them and set as input, output, etc. There's the clock configuration, which we'll get to that in just a bit. And then there's the configuration for the peripherals and also the modules, some more module definition within the device itself as well. So if we go back to the pinout tab, you could configure if you had we're using the ADC in your design, you would select it here. You could select the inputs that you're going to use and some other features inside the ADC. There is also a clock trim controller as well for trimming the clock, internal clock for USB in particular, CRC. There's a free running watchdog timer. You can activate it. I2S port, you can configure it in here as well. There, the I2C, the infrared port, you can enable it here as well. Power management unit, we are going to configure the reset and clock control unit here. So we do have the high-speed input pin is connected to an external crystal. Also, the low-speed clock input is connected to a crystal as well, 32 kilohertz. So you can see where, since we set the clock unit up here, you can see where it's configured the pins here in a certain state. So green denotes where the pin's been set based on the module setting here. We could also, if we wanted to, we could select the clock output here. We're not going to use that in design, so I'm not. Real-time clock, we're not using SPI ports. We are going to set up the system. So we are going to debug this design, and we're going to use the debug port that's on the board. So you can see where it actually just configured those pins for the debug interface. And then the time base source is based on the sysTick. So the timer, you could set those up here. The UART, if you're using those, you could set those up here, or USART. And the windowed watchdog timer, if you were using that, you could set that up in this device. So that is all we're going to do here, except for there's an important step. We are going to use the 4 LEDs. And let's go ahead and open up the data sheet to see where those LEDs are. So this is the user manual for the evaluation kit. So PA8, 11, 12, and 15's hooked up to LED 1, 2, 3, and 4 respectively. So let's start with PA8. We're going to set that up as a GPIO output. 11 again as a GPIO output. 12 and then 15. So let's double check that. So that was 8, PA8, PA11, 12, and 15. Port A8, 11, 12, and 15. All right, looks like we're in good shape there. So the colors denoted here on the pinout, blue means that it cannot be configured, it's automatic. Green means that it's configured based on the settings you've made and the modules that you've selected inside the device itself. And then the yellow is basically we made the manual configurations. So that's what the three colors denote. So next we're going to go into the clock configuration tab. We can't see a whole lot here, so to zoom out, I'm going to select control on my keyboard and use the wheel on my mouse to zoom out. So now you can see the entire clock tree here if I scroll down. So the clock tree is only configurable per the functions or the modules that you've set up in the pinout tool itself. So we do have, an external high-speed oscillator, a low-speed external oscillator that we've set up and selected inside the pinout tool. So you can see in this mux here, right now by default it's set up to use the internal 48 megahertz clock. So we could tell it to use the external oscillator. We're just going to leave it in this default state. But you can see where you can configure the entire clock tree based on the modules that you've selected and the features that you're using inside the chip itself. So we're not using the flash memory controller, that we are using the AMO bus, of course, and that's using the high-speed clock here at 8 megahertz. You can see where it goes back through the AMO buses at 8 megahertz here as well. And then we're not using the flash clock, or I'm sorry, we are using the free running clock. We're not using the flash memory controller up here. So again, a lot of granularity here, and a lot of you can set up the entire clock tree here. Basically, you don't have to refer to the user manual to get this information. It's right here at your fingertips. So let's go to the configuration tab. So configuration tab, you have the general settings here. So we could go into DMA. So if you had a DMA channel via UART or some SPI port or something that you wanted to interface directly to memory, this is where you would set it up. And then also we have a memory-to-memory configuration tab as well. So next is the vector interrupt controller. These first four are selected by default in the tool. I do want to include the reset and clock unit and the global interrupts for that. So I'm going to select that and then hit apply and then OK. So again, this is the setting for the reset and clock unit. So this is where you could set up a clock trim adjust value from the get-go for your internal 8 megahertz oscillator. Here's your vector interrupt control settings where we've already enabled the global interrupt. DMA settings would show up here again and with more detail. And then here's our GPIO settings. So So here's where under GPIO settings, we have a GPIO tab, and this is where we've assigned our LEDs to these 4 pins. So you can go in here and you can actually put a user label on it. We're going to name that LED 1. 11 was LED 2. 12 was LED 3. 15 was LED 4. So again, we set these as an output pin. So there are 2 different modes. You can do the push-pull, and then the way that with the hardware was designed, it is a push-pull configuration. There is the ability to do an open drain as well, and you can select internal pull-ups, pull-downs. We're not going to do that, and then uh, the maximum output speed for that pin is 50 megahertz. So we've left the default setting for all 4 of the pins. So I'm going to select apply, and then you could do the same if you wanted to assign, for your uh, reset and clock control unit. You can make your settings here. You can put a user label with the pins, and then you can't select change the input mode. You can select a pull up, pull down for those oscillator pins if you wanted to, but there's no need to. So then we have the sys tab where we selected the debug interface, and you can put user labels on those as well. So now, based on the settings that we've made in the graphical configuration tool, we go here to the project um, tab, and then we would generate the code. So now that we've generated the code, let's go ahead and see what was created. So we go over here to the Project Explorer, and it just a bit. See the firmware libraries that were included, the SimSys libraries, the startup codes here, includes and source for the SimSys library. There's a HAL peripheral, so you can see where all the code for each one of the peripherals is included here. So ADCs, comparators, I squared C, I squared S, etc. Then we have the include for the project itself. So here's the HAL library for initialization of the device. Uh, there's a loader script that's included as well, flash loader script. And then here is the main program that was created. So it did include a couple, the initialization header file, also the header file for the family itself. So we have to do a system initialization first. We'll dive down into that in just a second. Clock initialization and GPIO initialization. So when I open this declaration, it's going to go into the system and then initialization code. So this is where we've enabled the peripheral clock here, where the time-based source is coming from, the systic, if you recall, in the clock configuration tool. And then, there's 4 interrupts for the non-maskable vector interrupt controller. So after system initialization, you're going to go into clock initialization, and then, if you recall, we there is an external high-speed crystal connected, so we enabled that, and then also the oscillator states on. There's also the low-speed crystal interface is selected here and enabled, and then also the internal 8 megahertz clock is enabled, as well as the 48 megahertz clock is enabled here as well. So you can see where the system clock is actually coming from the 8 megahertz internal clock here versus the oscillator. And then you can see from the clock tree configuration where the AMBA bus is selected as well. So next is the GPIO initialization. You can see where the peripheral clocks are enabled here for all 4 of our LED pins. We selected as a push-pull output mode. There's no pull-up, and then the max speed on the port or the pin is set to 50 megahertz. And all those are done the same way. Okay, so that's basically what the initialization code does. So since we're going to be developing code based on the GPIO, let's go ahead and dive back into the GPIO initialization. So if we look here, again, the GPIO was initialized here, but we want to be able to set and reset those pins as well. So let's open this declaration and go into. It's going to open up the C file for GPIO for the device, and that's where it was initialized here, and it shows you how it's constructed to do the initialization. So if we scroll down here and we do a little bit, you can actually do a GPIO bit set, and you can do a GPIO bit reset. So those are the 2 functions we're going to use. And so I'm going to go ahead and copy this al GPIO bit set, and we're going to go back into the main program, and we're going to go into the where we're going to place our code here. So that's the first thing. So what were the arguments that we needed for that? So I think it was, if we go back there, so we're going to set a breakpoint right here. Just copy the whole thing. So the 2 variables we need to set up here is a peripheral. So a GPIO, and that was port A. And then we can actually use the pin name. There was a pin name created there. Yep. So if we go back here, the pin that's LE. We actually have defined those pins, or it created this header file to redefine those pins. at the pin names inside the graphical tool. So let's go ahead and copy LED pin 1. So that is the port that we're going to pass to, and then the pin. So let's go ahead, and what we're going to do is, like I said, we're going to do a trace configuration, or a trace demo here, where we're going to light up LED 1, and then we'll need to turn off an LED, and then put a delay. So let's go ahead, and we did a bit set. We're going to do a bit reset. So it found that fine. So we're going to do that for pin. So we're going to loop back around. The last pin that's going to be on should be LED pin 4. Nope, I was right in the first place. LED pin 2. So the next thing we're going to do here is we're going to want to instantiate a delay. So if you recall, when we set up the clock tree, we're using the sys. So we're going to go into the peripheral library here, and under the source code, we're going to select the sys, the how_sys.c file. So in here it's going to basically set up the system and the system's clock tree. Debugs included here. Your time source is included here. But we want to go down and scroll. We want to find the delay. So here it is. So this is what I'm looking for. We want to have a delay of so many milliseconds. So I'm going to copy that, and we're going to paste that back into our code here. And then, I don't know, let's just delay it by 200 milliseconds. See what happens. So we turned on pin 1, we turned off pin 2, so we can just copy and paste this. All right, let's put in some comments here. So we're going to turn on LED 1, turn off LED 2. All right, so we're going to turn on LED 1, turn off LED 2, turn on LED 2, turn off LED 1, and etc. Okay, to speed that up, I just went ahead and configured that, went away and configured it and come back. So what we're going to do here for to chase the LEDs, we're going to turn on LED 1, turn off LED 2, etc. until we get down here where we're going to turn on LED 2, turn off LED 3, and we're going to circle back around the while loop. So you can see where it's going to work here in a second when we compile the code. So let's go ahead and save that. And then we're going to go over here to Project Explorer. We're going to left mouse click on the project, and then we're going to actually build the project. So let's see what happens here. Okay, so we just finished compiling, and it finished with no errors, which is what we're expecting. All right, now that we compiled the code, let's go over here and let's go into the debug. So left mouse click on uh, the project again, and right mouse click, and then you can select debug as, go into debug configurations. Again, we're going to select GDB general debugging since that's what's supported. You can either select and let's go ahead and you can select the new launch configuration, or you can just double click on it. So again, the project's trace LED created a programming file. The debugger is automatically selected as GD link because that's automatically detected on the board. So I'm going to select debug, and then that'll bring up the debug perspective here in one moment. So again, when it starts to debug it, it goes into the reset handler. We're going to go and we're going to select the main.c program, and we're going to set a breakpoint right here. So after we set that breakpoint here, it should show up over here in the breakpoint editor. And then we can select resume, and it should run and then break on that instruction, and it does. So after we do that, we can select run again, and we can look at the board over here on the side, and we should see the LEDs blink again until it gets back to here. So I'm going to select the full board view right here, and I'm going to eliminate that breakpoint. And then we're going to hit run again, and should be able to see the LEDs trace or scroll. So that is starting an example from start to finish with the graphical tool, uh, creating the code, going in and actually creating an example piece of code. And I want to show you a couple more things in the tool next. All right, to show you what I want to next, we're going to end this debug session. So I'm going to pause it right here, and then I'm going to terminate it. So if you don't pause it and terminate it, you could get the board into an erroneous state. But we're going to go back to the Project Explorer here, and we're going to right mouse click on the project itself. We're going to hit Properties. So if you go into the properties for the project itself, you can see how the tool configures itself for the libraries, uh, the resources that are used, the build variables, environment, how it's set up, where the path, where the tools are created, where the debuggers, the path to the debugger, etc. There's other settings in here as well. So under the C++ build settings, you can see where the target processor, the family selected here, instruction set, other settings here, optimizations. This is at level 0. So, you can, if you wanted to make your code more efficient, you could go up in levels as well, but you have to be careful when you do that. So you have to know what you're doing. So other warnings, you can set warnings, debugging information here. What output files do you want generated? So you can actually do a dump file, hex dump here as well. So a lot of times those are useful for debugging your design as well. So I just wanted to show you a couple settings here for the compiler. Uh, it's using the GNU 11 compiler. The linker, again, that load script is set here in the linker that was defined here when we set up the project as well. And then, do you want to use a preprocessor when it's running assembler? And then you could include other paths here as well. So just wanted you to see where to make other settings in the tool, in the IDE as well, for optimization, libraries, etc. So basically, that's the end of this little tutorial on the graphic configuration tool and embedded builder. Thanks for joining me.